Alrighty, hello everybody and welcome to another one of these geometry of pattern sessions. So I'm sorry for making these like this. It really is a very shitty format, but it is what it is. Again, people tune in afterwards for the recordings, maybe they do, maybe they don't. Hello and welcome. My name is Kami Kirai. Hey, how are you doing? Today we're going to look at two concepts. We're going to try to keep it in the hour as well, in the pocket. Look at the orthogonal angle sumless. We saw this one before, but the idea pretty much is that if you have a solid, you add the sum, the angle, and a vertex, and then you multiply by the amount of vertices you have. So in the case of a cube, this would be 2 pi over 4, 2 pi over 4, 3 of them, 6 pi over 4, multiply by 8 because there's going to be 8 vertices in the cube, and we get this. And then in the case for the octahedron, there's going to be 6 vertices, and each vertex is going to be 4 pi over 3 because there's 4 triangles, right? It's going to be 8 pi. The sum, that means that inside, that's how much the angle is encompassing inside of the figure. And it's very interesting to me that these numbers, in the case of platonic solids, always add up to some multiple of 4. So I'm going to go into a little bit of a metaphysical theory in the way that, I don't know if we've gone over this too much, but yeah, it's a very interesting topic. I think I may have mentioned it, but didn't go into it. We're also going to be looking at half stars. It's this concept of extracting certain star patterns from inside of a polygon star. So in this case, we see that there's a sixfold 12.5. So we have this angle of 12.5, so we can use the internal angle for a star formula, right? And pretty much really fast discover that this angle right there is going to be pi over 6 or 2 pi over 12, pretty fast. Yeah, so right there. And so we know that that angle is going to be that, but we want to focus more attention on how these two colors interchange. So we can get half of whatever number we have. So if this is a 12, then we can get a 6. And in this one, we get an 8, and half of it is 4. So notice again the color change. And so it might be like a single star, but we can sort of extract from it this angle of, would it be 2 pi over 8 in this case, using again the internal angle for a star formula in my head. So we're going to look at these things today, so it should be fun. And yeah, so I turned off the comments for this thing, but it is what it is. And so we're going to be looking at the half stars first. So this thing about the half stars actually comes up quite a bit in the Islamic geometric world. This is how you might play around with what's expected and turn it on its head a little bit and get new, different, and original shapes. Sometimes, not always. But first thing we gotta take into account is how stars themselves work in an Islamic geometric context. So what I'm going to do, actually, not this one first, I'm going to inscribe the radial lines of a polygon. So I'm going to go ahead and inscribe. We're going to look at the case for the 8th, and then we'll look at the case for the 12th. But I'm going to try and make it intuitive and fun, right? It might not be either of those things, but it is what it is, and that's about it. And a while ago today, I was very inspired, and that kind of inspiration just dwindles. I don't know how to explain it. So I'm pretty much just going to connect the dots here. And then what I'm going to do is I'm going to inscribe the 8th 3 into this thing. So that means I'm going to go 0, 1, 2, and 3, right? I can choose any point and call it 0. So 0, 1, 2, and 3. Now there's 8 points, so that means that n is 8. And I'm going to jump 3, so that's a 8/3. And there's going to be your system. I'm going to go ahead and inscribe that. So, not very good drawing. Again, it is what it is. I leave it to the reader, to the people watching this, to make better drawings. But the intention is good, right? The intention is what counts. Oh, by the way, today we have on the board here the quote board. This quote by Kepler: "Geometry is one eternal shining in the mind of God." And the complete quote is, "That share in it accorded to humans is one of the reasons that humanity is the image of God." By the way, today is Thursday. It is 3:05 p.m. on January 28th, 2021. All right, so we have an 8/3 inscribed. From what we've seen before, we know what this angle is, right? We can use the internal angle formula, which I'm going to write here. The internal angle formula is, what was it? Pi times, no, it's not pi times. It's n minus 2k times pi over n. So this is the star angle formula. So 8, 3, so n is 3. So this, again, recap. The star polygon A3 comes in the form of nk, so we substitute here. We put n8. Go ahead and do it. So it would be 8 minus 3 times 2, that's 6. Over 8. 8 minus 6, that's 2, so 2 pi over 8. And that's the angle right there. By the way, shout out to, well, I forget his name right now on Instagram, but it's Alberto Grant. He is on the Discord server as Enkint. Dude, this guy, it blew my mind, man. He's from Italy and he's like, you know, he's been following the sessions. I remember watching this. Shout out, Alberto, man. And he just did this like web app, man. He's like coding these lessons and shit. It's amazing. It's beautiful. So shout outs, man. Shout out. It's so amazing, man. You should really check out that on the Discord server. My mind is blown. Anyway, we have the angle, we have the star. And so the thing is, what I want you to know is that usually in the Islamic pattern, you know, canon, it never actually looks like this. Like stars never look like the full line. It always breaks. There's always a break. So it's like you can watch the line come, hits on this other red line and jumps back out. It never is the case that these lines are just, you know, completely continuous. Now, Craig Kaplan, I'll write that name down. If you want to, Craig Kaplan, you can put that name onto YouTube, put that name onto Google, maybe write that down and like type it a little bit like Islamic pattern, some shit like that. But Craig Kaplan, he has this wonderful, you know, video lecture on how to understand these from a coding perspective. So he has coded several different shapes and like whatever, right? So he actually, I know that, I haven't studied his work so much, but I know that he has actually a nomenclature for the difference between what you'd say, like, there's a difference in a way between this 8-2, there's an 8-2, and then a difference between that and this, where it kind of like breaks. I forget how he spells it, but he does write these two differently. So they're the same shape, they're the same 8-2. But this one has a little break in there, sort of like the line comes in, hits, bounces. So I just want you to note how the point of breaks, when the line comes in from a red line, hits on the red line, and then bounces out. So these radial lines are where the line chooses to, like, you know, bounce back out. So this is also why I prefer to understand these patterns in terms of circles and not in terms of polygons, because polygons by themselves don't necessarily include this type of information, the information relating to where the reflection is going to happen. Because as you can see, on this line, there's going to be an angle that comes in there and hits, and an angle that comes out, and they are the same angle. So this is sort of like the analogy with light. There's actually a property of light when it bounces off a mirror. The angle in which it comes in is the same angle in which it bounces out in. So that's pretty interesting stuff. So, all right, we have an 8-fold star, right? 8-fold meaning that, you know, we can take like a slice of this thing, and that's like the pattern. It's an 8, right? It's inside of this slice, and this slice goes around 8 times. All right, so we want to make it half. So what's half of 8? That's 4. So what we do is we simply take into account 4 of these bounces, right? So we can take away, you know, we can take away 4, just like that, just take them away. And this pattern, this star actually comes up in the canon in this, there's a very typical pattern, but pretty much like this, right? So there is a way to make a 4-fold star, and this actually would be a 4-fold star, right? Now instead of the happenings being on this slice, it's now on this slice, which is a 4-fold. You know, it happens 1, 2, 3, and 4. And if you're familiar with origami, this might actually look familiar. This is a bird base, right? So origami and Islamic patterns coming into play here. Very beautiful thing. So again, half stars, interesting stuff. This is now going to be what we would call a fourfold 8-3. Now, not all of them are so interesting. Fact is that, for instance, if we were to make this one fourfold, we would just get a square, right? The 8-2 and a fourfold pretty much is what it is. It's just a square. But the fourfold 8-3, that's a little different story, because we have a star, but it's 4 inside of the 8. So if we were to, like, you know, maybe this is not the time and place, but we can make then this angle, which is the angle of contact here, we can simplify it, see? It's 2/8. So we can simplify this into pi/4. So this is an interesting little thing, that star polygons always are going to be even. So by taking them into half, we're sort of simplifying and going to the world within. So we're going from the world of 8 into the world of 4. I just got this feeling that if I was in a classroom, the students would be looking at me like, dude, what? I know, and it's weird to have no feedback, but it is what it is, right? So we go from the 8 world to the 4 world, and we have now this, pi/4. So, you know, if we actually look at the list for the force, so let's go ahead and like look at the list for the force, and we're going to see how this is like in between. So we're going to apply this to the 4 now. 4 doesn't have any stars, we can still apply this though. So we can apply first, let's go ahead and just put the 4 into there. So we're going to put in 4-1 and 4-2. So pretty much this is what we're going to get first, 4/1 in the nk, so we substitute there 4 minus 2, that's for the 4-1, times pi/4, don't waste time, we get 2 pi/4, right? And then the other one would be 4-2, so that would be 4 minus 4, would it? Yeah, I mean that just pretty much, yeah, leaves it with 0, which is just a straight line. But what this implies is that there's going to be, you know, a pi/4 and a 3 pi/4. You know, like, not underneath it, but, you know, if we wanted to, you know, find the angles of this thing working on. It's interesting also, like the pi/4, and over it would be 3 pi and then pi/4. So if we multiply, if we take this angle now and take it into the 8th world, we get that this 3 pi/4 actually would be 6 pi/8. I'm multiplying it by 2. I'm actually going now this way, very confusing. And then this one also multiply by 2, and then that would be 2 pi/8, which is that. So we can actually then sort of retrace our steps in the case for finding which star this belongs to. So we can see that 6/8, so how much 2's are we taking away from 8 to get to 6? There's only 1 2. So then this angle pertains to the 8/1 star. I know I'm good. None of this is weird, man. This is very esoteric stuff. It's nonsense. But this is the way to get like a close approximation to what is happening. We don't need to know these things. That's what's beautiful about it. You don't need to know any of this and still make beautiful patterns. And but yeah, so we can, like, you know, find that, and then we can sort of look at this. How many 2's are we taking away from 8 to get to 2? That's 3 2's, right? So that's the 8-3. So then this angle is for this star, just as much as this angle is for this star. I know this is weird. I know this is weird. All right, let's look at another example. Let's look at the example for 12. Usually, these examples are not, like in the canon of Islamic patterns, these will come in the form of either in the 12th world or the world of 10. Also in the 8th world a little bit. If you want an example of how it would look in the 12th world and 8th, because that will happen, you can look at Richard Henry Art's recent pattern that he did, where it's like, it has this irregular heptagon in there. That's a good example of a half star sort of involving itself into the pattern. So we're going to look at 12 now. Alright, let's look at 12. So I'm going to put in 12 points here. So then I put 6 points, and then I sort of imagine an arc and put a point in between. So 12 points on a circle, what do we call this? Simply 12. That's a bracket, very shitty bracket, but it is what it is, right? So we got a 12 bracket, so that's 12 points around the circle. That's how many points we have in our circle. Imagine a circle. And let's like think about which star we would like to have. So now because we're in 12 world, whatever we're gonna get now is gonna be a sixfold. So this is 12-fold, but we want to get the half star. So half of 12 is 6. So we're going to go get a sixfold 12. Alright? So now we get to choose which sort of star can we do this for. So within that example I was mentioning of Richard Henry's, let's look at the case for the 12-3. I think that was a 1. I know it's not 12-5, and it can't be the 12-4 because 12-4 would be just, that is sixfold. It would just be a hexagram. So we do have to go into this world of the 12. So for the 12-3. Yeah, it is a 12-3. Alright, so again, 12 points. Let's change up the color a little bit over here. So now I'm going to count, 3 vertices. So 0, 1, 2, and 3. Draw a line. Oh, wait. Before I do that, I'm going to actually inscribe the radial lines. Which, the radial lines, because it's an even number, will just go across very nicely. By the way, this half star system is also how you get an odd number star to be parallel, to be made up of parallel lines. This is the only way to do it, actually. This is also, excuse the truck. Yeah, so pretty much this, right? We have now 6 lines going all the way across. I think it would be 6 lines. Yeah, it's probably 6. All right. So, no, not black. What we did before. Yeah, let's do green because the formula here is in green. So 0 to 3. 0, 1, 2, 3. 0, 1, 2, 3. So, we can do the mod thing. We're pretty much just like doing the, mod 12. Right? So we're starting at 0. So 0 plus 3 is 3. And then 3 plus 3. Because K is pretty much like how many steps we do, right? So now we go 3 plus 3, that's 6. We can do it. We can actually label all of the points. Let's go ahead and label all of the points just to make this exercise. By the way, again, it's brought to my attention that kids watch this. So when it gets to 12, it's 0. There's no 12. Mod 12 means no 12. 12 is 0. All right. So we go to 3. From 3, go to 6. From 6, we go to 9. 6 plus 3 is 9. And then 9 plus 3, that is 12, which is 0. So that closes. Alright, so we have our first system. We see that actually is a square, a very shitty square, mind you, but it is what it is. So now we're going to start the system. Instead of starting at 0, we're going to start at 1. So I'm actually going to erase these as I draw them for a space. I'm going to add on here just a little thing, k equals 3. Right? So just to keep in mind. So 1 plus 3, that's 4. 4 plus 3, that's 7. 7 plus 3, that's a 10. And 10 plus 3, that's a 1. Why 1? Well, because we're mod 12. So whatever number we go over 12, we got to put in whatever we go over. So 10 plus 3 is 13. And 13 is 1 more than 12. So we're going to look at that. So we're going to start at 1. So 1, 4, 4, 7, 7, 10. And then 10, 1. Alright. Now we're going to start at 2. So 2 plus 3, that's 5. 5 plus 3, that's 8. 8 plus 3, that is 11. 11 plus 3, that is 2. Is it 2? Yes, it is 2. Back again. So 2 ends, 2 begins. Cycle closes. So we're going to go 2 to 5, 5 to 8, 8 to 11, 11 to 2. Alright, we got our 12-fold star here. Right? We got our 12-3 going on. Now, this 12-3 is 12-fold. Again, we have the slice, right? It's all happening inside of this slice. I'm just going to do 12 of these slices. We're going to go half. We're going to get 6. So what we're going to do is we're only going to care about, we can sort of highlight this to make it make more sense. So I'm going to go ahead and just erase some of these lines. I'm gonna just ignore half of them. So pretty much I'm gonna ignore this. I'm not gonna, yeah, pretty much just erase it. Erase one, and jump one, erase that one too, and jump one, erase this one too. So now it's 6, so we gotta take away some of these things. So whatever's not working for us, got to go. So this guy's got to go. This guy goes here. But, you know, interestingly enough, actually this line sort of communicates with this one. You see that? You see how it's not, we can't take it away completely. Where's my green? Because this one completes with that. By the way, I just listened to this album Blonde by Frank Ocean. I had to listen to it, man. It's so good. It's so fucking good. Loving that album. I'm gonna listen to it more. I don't know why, man. It's so bittersweet. It's nice. So yeah, you can see that jumps here, jumps there. Not using this, not using this, not using this, this no, tampoco, these no, neither. And there we go. Now, it's interesting because I shouldn't have taken away this line. I shouldn't have taken away that line. It's sort of like I did it to highlight whatever, but let me put it back. I'm going to put it back in another color though. Just again, no, I shouldn't. No, I'm going to put it in the same color. Nah, but I erased it, so I gotta pretend that I'm committed. Right? So yeah, we take away these little excesses there. I feel like I was way behind on that album too. Just like it's I don't know for when that released, when that dropped. But I know it was big, everybody was listening to it. And now I'm listening to it, I'm like, damn, it's just actually pretty good. Anyway, so we have the 6-fold 12-3 here right now. This is what it looks like. And so again, we can just pretty quickly use this formula to get what this angle is right there. So that angle, what's it gonna be? 3 times 2 minus 12. 6 minus 12 is 6. 6 pi over 12. And that pretty much, you know, pretty fast we get that that's a right angle. So these are right angles. All of them, right angles. So it's a very nice little thing that we can have like this star with right angles, right? So we can make like a 6-fold right angled star. Pretty cool. So, you know, where does this put us though? Like where are we now? Well, if you were to like take this star and like, you know, get a little sequence going on, say that you had, you know, just a bunch of hexagons, you know, just to say whatever, we could, like, instead of getting the, you know, we could get the 666. 666. I was listening to Iron Maiden yesterday, man, going back to my memories. I was listening to like Woodstock, Primus. You guys know Primus? Primus sucks. Yeah, Primus, beautiful. Anyway, we get the 666 right here. We can take this star and put it in the midlines. So pretty much like we're shooting right angles here. So this line comes in and connects, right? But this is going to be a right angle. Comes in there at a right angle, bounces back out, bounces, right angle. Yeah, pretend that it's right. And so what's interesting is that we get like these weird shapes in between. We're not going to get a hexagon here no more. Let me just go ahead and just do it. So, you know, I have like these colloquial names for these. I call this the fatty, right? This is the 12, the 6, 12, the 6-fold 12 fatty, and there's going to be the 6-fold 12 slim. It's like a fatty and a slim guy. I don't know how the, you know, Laurel and Hardy, you know, that old school TV show about, you know, these two like buffoons, pretty much just like stumbling through life, just like, you know, whatever. And so, yeah, we get this. So, pretty interesting shape in that, you know, it's a great way to break away from the norm. So, if we wanted to like understand this to be like in the 6th world, so we're getting in the 12th world, so we want to understand it in the 6th world, we have to divide it in half. So this would be a 3 pi over 6 in the sixth world. This angle is 3 pi over 6. Still a right angle, but we're in the sixth world. So, interestingly enough, if we go now into the sixth world, I'm going to take away this little title, it's 666, number of the beast, hell and fire is going to be released. And we go from there and sort of like, you know, inscribe this thing, our sixthness, right? So, you know, we can start with the 6-1, see where it goes until we get to 0, we don't include the 0. So, okay, we get to 6, so first is going to be 4 pi over 6. That's going to be for this one. No, that's not true. 4 pi over 6 is going to be simply for the hexagon. Yeah. And then 2 pi over 6 is going to be this. So I want you to notice that this star, got it. This star is 3 pi over 6, which is sort of between these two. You know, like it's a wedge between this 4 and 2. We get this guy, the 3 pi over 6. So it's interesting to think about that the odd numbers in between the star systems are actually stars on their double, right? Like this star is actually the 12-3, but it's actually inside or like in between the lines of the sixthness. So it's a very beautiful and interesting concept. We can like, you know, take this up a notch. We can like find whatever fold we want to work on. Oh yeah, by the way, there's going to be one more 6-fold 12. You might as well inscribe it, right? What do you guys say? Yeah. I can't hear you. I really can't hear you. I could be just talking to myself right now. And I guess that's fine. What time is it? 3:27. We got time. We got time. And I should maybe like let you guys know when I do these. But yeah. Okay, so now we're going to find the pi over 6 star. The fatty, the slim. We found the fatty that's in right there. It's this one. I go for the slim. It's pretty much like understanding that we're working with this sort of shape and just like extending the angles of this thing. So instead of it being 2 pi over 6, it's actually a 3 pi over 6. So it's a little broader and broader. B-R-O-A-D-E-R, broader. I used to get asked a lot like, where did you learn English? And I always tell them, you know, music and movies. That's like the most boring answer, right? But it's true. I mean, I never lived abroad, but I watched too many movies and listened to too much music in English. And, you know, in a way, it's kind of embarrassing because I think I speak and understand English more than I do Spanish, which is my native tongue. But I love both. I love both. I think in terms of both, and I love more the poetry in Spanish than I do the poetry in English, but you know, whatever, so it's a takeaway. So now we're going to go for I'm going to take away this too. So why can't we get the 12-4? So what if we get the 6-fold 12-4? I'm not saying that this isn't like possible, let's just look at it. So what angle would that be? We put K to plug it in here, so 4 times 2, that's 8. 8 minus 12, that's 4, so 4 pi over 12. We take that into the sixth world, right? We divide it now in half. It actually can be simplified. And we would get 6, no, shit, no, it's 2 pi over 6. And, you know, this number is even, and this is a 6, so this actually is already in our 6 system. We don't need to do it as a half star. This already is the star in the 6-fold. What we don't have is a 12-5, right? 12-5, what would that be? What would 12-5 be? So 5 times 2, that's 10. 12 minus 10, that's 2. So we get 2 pi over 12. We take that into the 6th world, right? We take it from 12 to 6. So now it's going to be pi over 6. This is going to be our angle. But we got to build it. So 12 over 5. So we start in 0. I know it's a little messy here. I should maybe erase it? Maybe? What do you guys think? Yeah, okay, I'll erase it. No, too much time. Alright, let's just stick with this. We can see sort of where the points are anyway. So we're going to start with the system. It's actually going to be unicursal. So maybe I should like make space for myself. I'm going to write this over here. N minus 2k times pi over n. The internal angle formula for stars. Beautiful formula. And yeah, that's a newly discovered thing. So pretty proud of myself for actually contributing something to mathematics. And so yeah, we start with 0. We had 5, so that's 5. 5 plus 5, that's 10. 10 plus 5, that's 3, because we're mod 12. Right? So whatever number we go over 12, we take away. So 3 plus 5, that's 8. 8 plus 5, that is 13. So that's 1. 1 plus 5, that's 6. 6 plus 5, that's 11. 11 plus 5, that's 16. 4 over 12, so that's 4. 4 plus 5, that's 9. 9 plus 5, that is, what is it, 13? 14, 2, so that's 2. And then 2 plus 5, that's 7. 7 plus 5, that's 0. Now we're back to where we started. So it goes first 0 to 5. 5 to 10. 10 to 3. 3 to 8. 8 to 1. 1 to 6. 6 to 11. 11 to 4. 4 to 9. 9 to 2. 2 to 7. And 7 to 0. So this would be a 12-5 star. Very, very messy. But, you know, maybe I should have talked about this before. I changed the colors here. But we only care about, like, not that we only care about, but it's really worth taking into account only the first instance of an intersection. Right? So what that means is I'm going to take away everything that goes over the line. So if my line goes, hits my line, I'm done. Like that's all I need. That's all I need from this. So I'm just gonna take away all these. So take away there, take away this, take away here too. So I just really care about like the petal shape. So I'm gonna take away everything that's not a petal, and then I can just inscribe whatever. Fucking children's music, man. Just so you get stuck with it. Must be a really cool feeling not to like develop something that's really catchy, like a little song that's like everybody can't help but sing along. I guess that's what Danny Elfman must feel like. By the way, I understand that the audio is pretty crap because I'm standing all the way over here, the microphone is all the way over there, but there's like this bellowing echo in this room, so it doesn't really matter. So this is what I was talking about when I talked about Craig Kaplan. He understands that these stars are truncated. You don't go the full line, and pretty much just like the line goes, hits, and bounces back out. And so you get like these petal shapes, right? You get these petal shapes and an internal star. Pretty fun stuff to think about. But this is what we're focused on right now. So we want to make this the sixfold. Instead of making it like this, I'm going to broaden our horizons a little bit. So I'm going to take away everything, or rather, maybe I should write it in another color instead of taking it away. No, I'm going to take it away just to be clear that, you know, this is what we're working on. But in this case, there's going to be no intersections as before, where I kind of like have to be careful what I took away. In this case, I can pretty much clearly see that these are pretty independent shapes, which is kind of interesting to think about, like why is it independent and the other one not, but we're not going to worry about that for now. So we're going to take away one of these. And then I'm going to complete it. How are we doing on time? Alright, yeah, we still got time for the orthogonal list, so beautiful. I think we're right on time today. Surprising. I could go with this change of pace, man. Alright, we got that. So now we have a six-fold 12-5. It looks a little bit something like this, and that's a slim gem, right? This is not a slim gem, but that's like the slim star. It's skinny. So we can put this system inside of the 6-3, the 6-6-6, or we can put it inside the 6-3-6-3, right? So just as well as we have, you know, this system of hexagons, we can also inscribe here a little system of hexagons and triangles. And we could still, like, you know, get to something. Interestingly enough, this pattern right here, we could also notice that we're sort of using this star. Which star is this, by the way? Ask yourself, like, what angle would this be? It's inside of this contact. So you can follow along the line. You go like 0, 1, 2, 3, 4. So this is a 12-4. So what angle is that? Well, 4 times 2, that's 8. 12 minus 8, that's 4. 4 pi over 12. That's yeah. So this is an equilateral triangle. Rather, 4 equilateral triangles. Nice. And then, you know, pretty much like everything spreads. And the bounce, it happens there, it's related to, also interesting, we get a 4-fold star here. So the 12, we can actually make 4-fold stars as well. We don't necessarily have to make them all be 6-fold. We can actually get 4-fold inside of 12. I haven't thought about it like that. That's interesting. That is very, very interesting. We could actually make the 12-4 be 4-fold. Ha! That's interesting, man. All right, we're gonna not worry about that so much. Anyway, we can put this star with the pi over 6 angle into this thing. So just taking again into account the midpoints of the edges. Dude, I hadn't thought about it. That's wonderful. I hadn't thought. I'm gonna experiment on that in AutoCAD tonight. See how that goes. And so we can put in the pi over 6 angle. Pretty slim. Again, not exact, but here's an interesting little tidbit. We're going to use like the radial lines here to note where this is going to jump. So this like comes in and then jumps back out. And so it does here. And then this one comes back and jumps out. And this one goes there and jumps back out. Well, yeah, pretty crude drawing, yeah, pretty much. A very, very, very tight little shape there. Yeah, it's like a 3-fold 12 in a way. Like this little shape would be what we would get if we actually extended these. Which is pretty interesting if you think about it. Because this little shape right here would be the 3-fold of this 6-fold 12. So, you know, we can play around with the multiples of the thing. That's pretty fascinating, man, how we can like keep going. So we can even make like a half star of this already half star. We can even see it in the tiling. So that's pretty cool. Actually, what gave me that idea was watching that. This was the first one we did on the PSTA workshop. I think that was like class 6, and that one was class, I don't remember. But all these 3 today are from the Princeton School Traditional Arts workshop. Which I actually have to get back to them and ask for feedback. I don't know if the students liked it or not. I know that probably was too hard at first, but I think they got the hang of it in time. I'm not going to presuppose and actually call them. But anyway, we get this little shape, weird shape. It's like a weird octagon there. Kind of interesting. Usually this 6-fold 12 comes in the form of the 6-6-6 more than the 6-3-6-3. Right, this would be the 6-3-6-3. So, you know, depends on where you want to put your star, but it's a great way of like playing around with the expectation of the viewer. Sort of like subverting expectations, but still retaining true character. Because we're working with whatever world we inhabit. Pretty interesting stuff. Let me think about this one though, because we can make this 4. But yeah, I think we need the full extent of the star to make it true 4. So I'm not going to worry about that now. But yeah, interesting, right? I mean, I hope it was understood, the idea. And how you can like find, like, you can make them, I don't know, you can always like get to a further world. And the thing about taking this to 3 would be that now you would get a fraction on top. So if we take this angle to 3, as we did here, sort of like, if I get a new color, So this would be a 3, 12, 5. And so the angle of this in the 3 world would be half of this. So it would be almost like 0.5, let's say. Just because we don't want to put a fraction on top of fraction. We could though. I mean, we could put like half of pi over 3. Pi over 2 over 3, so we can take this. Yeah, pretty much. I mean, we're saying the same thing. You can also write it as 0.5 pi over 3. If we, so, half of pi over 3. If we want to take that into the 3 world, so this, whatever, we want it to be in the 3 world. We don't really need to, so screw that. Anyway, so we're going to leave it at that for today for the half star topic. I think it's a very cool topic. You should play around with it. There's many things you can try. And there's also a great way of subverting the audience's expectations. You can also go higher. So instead of going from 12 down, you can go from 12 up. So you could take your number that you like, and just get your list. So for instance, let's do a list for the 12, just because it's a nice little thing to go up on. So 12, we're going to start with the 12-1, 12-2, 12-3, 12-4, and 12-5, and that's pretty much the only stars that we have. All of these, of course. I am the worst at drawing brackets, remember. 12-1, 12-2, 12-3, 12-4, and 12-5. We substitute here, so this one would be a 10 pi over 12, 8 pi over 12, 6 pi over 12, 4 pi over 12, and 2 pi. So notice how we're missing 7, 5, 3, 5, 7, and 9. And I guess 11 in a way. Oh, that's a little bit too big, right? I mean, maybe. But we look for instance, let's just get this one. Let's get the 5 pi. So we wanted to get the 1.5 here. So what would that be? That would be a 5 pi over 12. Now in terms of star, that makes no sense. So we can find this angle in the star higher to it. So we multiply this by 2. What do we get? We get 10 pi. By the way, this is times 2 for both. We got to multiply the top and the bottom. So it's almost like this. We want to keep it the same thing. So 10 pi over 24. How many pi's are we taking? How many 2's are we taking away to get the 10 from 24? Well, 24 minus, we get the difference. So 24 minus 10, that's 14. So, no, that makes no. Yeah, so that's 7. Is it 7? It might be 7, yeah. Because this is what we're taking away. So 24 minus 14 is 10, so yeah, 7. So, 14 divided by 2, that's a 7. So that's our K. So then this angle belongs to this one, which in turn belongs to 24/7. So if we had a 24 gone and did the system of 7, the mod thing and adding 7 and connecting the lines, this is a star. It's right between here. And we could replace this star in this 12, for instance. And we could get a different arrangement, and the angles would be different and the shapes would be different. Everything would be different. But it's a cool way of bringing different lines and patterns into this thing. And of course, we would have, in order for that to make sense, we would have to make it 12. So, you would have 24 lines, but you only focus on 12 lines because you're interested in the 12 world, right here. So, a fun way of getting these angles would be simply multiply by 2. So as you can see, number 2 comes up a lot in this little sequence of this world. What time? All right, we got 10 minutes. Damn. All right, went a little bit over. This half-star topic, man, it's really something. But let's just look at this thing. I think we already went over this. I think it might have, but it's a very cool, interesting little topic. For this one, we're not going to worry so much about the star formula as we're going to worry about just the polygon formula. So for that, we're simply going to be n minus 2 times pi over n. So as you can see, I pretty much just took away the k, because k in this case is always going to be 1. No stars in this little system. Only that, the internal angle formula. All right, good. So let's first look at the case for the, shit, have we done this already? Nah. Well, let's just do it because I'm gonna work on the assumption that nobody has seen this before. Maybe, man, I should watch these myself. All right, oh yeah, all right, shit, all right. So first off, we're gonna start with, well, yeah, maybe I should get a list. All right, let's start with the names. Let's start with the platonic solids, of course. So the tetrahedron, the hexahedron, the octahedron, the dodecahedron. I think this was one of the first topics we watched, but tetra, hexa, octa, dodeca, and icosahedron. So by recap, what does hedron mean? So where do I put this? So hedron means face. So these numbers, or rather these little prefixes, are the numbers. How many faces does this shape have? So it's tetra. Tetra is 4. So it's a 4-face. Hexa, that's a 6-face. Octa, it's an 8. Dodeca, it's a 12. Icosa, that's a 20. Each of these also just so happens that it has a Schlafly symbol associated with it. The tetrahedron is the 3.3.3. 3 triangles to a vertex. Yeah. Hexahedron is the 4 squares to a vertex. Octahedron is 3, 4 triangles to a vertex. Dodecahedron, 5, 3 pentagons to a vertex. And the icosahedron would be the 3, 5 pentagons to a vertex. So Schlafly pretty much he caught wind of this. So instead of writing these like this, because they're the same, he actually devised a little very ingenious little system. I'm going to actually write it over here now. So this one we write as inside of the brackets too. Get another color. 3, 3. So it's 3 triangles. The 4, 3. 3 squares. 3, 4. 4 triangles. 5, 3. 3 pentagons. And 3, 5 for the icosahedron. We have gone over this, man. I'm getting like flashbacks. But yeah, so pretty much why I do this is because we get the duals. So we can see how these are interchanged, right? The 5, 3 is different, the 3, 5 is different, 4, 3, 3, 4, 3, 3. Alright, so we can use the formula which I just erased. Right over here. N minus 2 times pi over n. You can use this formula to see what angle and then multiply that by how many there are. So for instance, this one would simply, if we wanted to unfold the thing, it would look something like this. Well, now this is pretty much like how it would look by itself, like from a side view. Just assuming that you can see how underneath that's sort of happening. There's a triangle at a base, triangle at a face, triangle over there, and triangle in the back. So 4 triangles, right? 4, right? So we also have the amount of faces that we're going to work on. We're sort of I think we have to know this, man. It's just bugging me that I'm sort of repeating myself. But the metaphysical thing is that, well, we gotta add them up. Anyway. Alright, so at a vertex there's going to be 3, 3, so what's the internal angle of an equilateral triangle? So because we're going to be working on with 3 shapes, in this case, actually, I can actually make a little list. So whenever we have a triangle, the internal angle for that is going to be pi over 3. Whenever we have a square, the angle is going to be 2 pi over 4. And whenever we have a pentagon, the angle, not over there, the angle is going to be 3 pi over 5. Okay? So from here we can sort of see how many times we're going to multiply and then go a little bit further from it. But this is going to help as well. We're going to get there. All right, so we got the tetrahedron. Now the question is, like, how many vertices does it? Well, no. Easy. First off, what's the sum of the angle? So if we have this shape, what's the sum at a vertex? So if we had, like, the tetrahedron in our hands, we could look into it like a room in that corner. What is the angle of that corner? By the way, that angle at a corner is called the orthohedral. Orthogonal? No, it's not the orthogonal. It's dihedral. Oh, shit, at the beginning I wrote something else. No, but it's the dihedral angle. It's the angle that's like between the faces, but sort of like we're adding up. It's like picturing a sphere. It's like we're almost like putting a sphere inside of the shape and sort of like adding up what that would be in a way. So yeah, the dihedral angle. I think no, the dihedral angle is the rise between faces. So I think then it would be the dihedral. Now would it? Nah. This is another type of angle, man. I'm not even gonna like bother, but you can just anyway. So each of these vertices, we'll write this the vertices. So we had 3 pi over 3, so we're going to multiply. There's going to be 3 of them. So this is pretty much going to be like 3 pi over 3. Pretty convenient. And then we multiply by the amount of vertices it has. So it just so happens that the tetrahedron has 4 vertices. So we multiply this by 4. So 4 times that. So 4 times 2, that's 12. 12 over 3, that's a 4 pi. Now this is pretty interesting to me because what is going to be the implication for me at least is that inside of all these shapes there's going to be an amount of tetrahedrons. So it's like in the flat world we get an amount of triangles. So a square has 2 triangles, a pentagon has 3 triangles, etc. But in the 3D world it's almost like what is the amount of tetrahedrons your shape has? We're going to look at that in a bit. And so this is the exciting thing about this thing. Alright, so we have 3 squares. So what's the angle of the square? 2 pi over 4. So there's going to be 3 of them. So I multiplied this 2 times 3, so that's a 6. How many vertices does a cube have? Well, we could draw it. Or we could just look at the dual of it. Because the dual will have as much bases as it has vertices. So this is going to be a change arm, but look at this cube. So I can put like 4 fingers underneath and 4 fingers on top. So a total of 8. Wait a minute, 8. It's going to be 8 here too, right? So it's like, all right, we got 5 minutes. Damn. All right. All right, yeah. So now we got 8. So it's going to be 8. This 8 por 6. Oh, me escuchan todo. Yeah, 4 times 3. No. Then we have 4 triangles here, so we got this. So at a vertex we're going to have 4 pi over 3. And then this one, if we sort of like pictured it, we actually are going to have 6. So the dual has as much face as it has vertices, what a dual is. So for this one, it's going to be 6. By the way, the number I'm multiplying here again is the vertices. How many vertices does the shape have? That's how many times we multiply this angle, because this is what it is at a corner. So anyway, 6 times 4 over 3. 6 times 4, that is 24. 24 over 3, that is 8. Alright, so the dodecahedron, 5 3s. So it's 3 of these. 3 pi times 3. So 3 times 3, it's a 9. So 9 pi over 5. How many vertices does a dodecahedron have? Well, its dual is the icosahedron. So as many faces as the icosahedron has is how many vertices the dodecahedron has. So 20. So here we write 20 times 9 pi over 5. 20 times 9, 180. 180 over 5. What is it? Is it a 90? No, it's a 36, isn't it? It's a 36. Yeah. And then the icosahedron, so the icosahedron is 3, 5. So that's 5 of these at a corner, so this one's going to be 5 pi over 3. How many vertices does an icosahedron have? As many faces as the dodecahedron has. So 12 times this 5 pi over 3. 12 times 5 is 60. 60 over 3. That's pretty fast. It's 20, isn't it? Yeah. So you can see how all of these are multiples of 4. Isn't that something? Like, it's almost as if the tetrahedron is how many times is how many tetrahedrons can we inscribe into the cube? Well, 3 of them. It's like this one fits 3 times into this. This one fits 2 times into this. This one fits 19 times. That's interesting. 19 times and 5 times. No. Yeah, 5. This is 19. This is 9. Yeah. Okay. So pretty much what I'm saying is, maybe I should it would be cool if I could select it and push it. But anyway, so what I'm saying is that this is equal to 1. Well, this is like our unit. Like the tetrahedrons are units. It's like what the universe is made up in 3D space, if you will. It's like the metaphysical aspect of it. And this also happens to be the surface area of a sphere. That's also interesting. That there's this relationship between the tetrahedron and the sphere. So we could think of this as equal to 1 sphere. So how many spheres is this? This is 3 spheres. This is 2 spheres. This is 9 spheres. And this is 5 spheres. So I think that's pretty cool. I think this is pretty cool. Because it's always going to be a multiple of 4. So this is, pretty nice. So, yeah, pretty much that's it for today. We're going to look at more Archimedean solids later. But yeah, let me just do a little quick drawing for you. Tetrahedron. A cube. An octahedron. This is a very crude drawing, man. One, two, three, four. 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4. 1, 2, 3. Yeah. So this is the tetra. This is the cube, the hexahedron, the dodecahedron, the icosahedron, and the octahedron. The 3, 3, the 3, 3, 4, 3. This looks like a 9. 4, 3, 5, 3, 3, 5. So yeah, pretty cool, no? How many spheres is these? And there's also a little exercise you can try. I haven't tried this very much, but you can get these shapes, and then the question is, well, can you make a system? Just as much as we can connect the lines for these shapes, and just as much as we can connect this point to that point and get 3 triangles, and just as much as we can connect this point to that point and get 2 triangles, we can do a similar thing inside of these shapes. It's difficult and it's weird to do because it's in 3D space, but there is a way to tie the corners up to each other in such a way that you get this amount of tetrahedrons inside of it. It's very weird to do, but it's a very fun exercise if you want to like draw some 3D stuff. And yeah, fun in it. So I'll leave it at that. Thank you all for joining again. And next one's going to be on Sunday, maybe, perhaps, I don't know. I got a lot of work to do. And yeah, I'll catch you then. So take it easy, enjoy, and take care.